The animal didn't cross the street because it was too tired. How does ChatGPT know that it refers to the animal and not the street? But change one word, it was too wide, and suddenly it refers to the street. The answer is a single equation, just 4 matrix multiplications and 1 softmax. It's called attention, and the 2017 paper that introduced it was titled with remarkable confidence, "Attention is all you need." They were right. Every concept we've built across this series leads to this moment. Episode 12, Attention is all you need, the math that powers modern AI. Every word starts as an embedding vector, a point in high-dimensional space. Remember from episode 10, each word is mapped to a dense numerical representation, but a single embedding can't ask and answer questions simultaneously. So we create 3 different views of each word. Query: what am I looking for? Key: what do I contain? Value: what information do I carry? Mathematically, each is just a matrix multiplication. Q equals X times WQ, K equals X times WK, V equals X times WV. Let's see this concretely with our 4-token example. Our input matrix X, with 1 row per token, multiplied by the query projection WQ, produces the query matrix Q. Each row of Q is 1 token's query vector. These projection matrices are learned. They start as random noise and are shaped by gradient descent, just as we saw in episode 2. The model discovers what to query for and what to advertise through billions of gradient updates. In the real transformer, with D model equal to 512 and DK equal to 64, each projection matrix has 32,768 parameters. 3 projections give us 98,304 parameters per attention head. Now comes the key insight. To determine how much one word should attend to another, we compute the dot product between query and key vectors. Remember from episode 1, the dot product measures similarity. Vectors pointing in the same direction yield a high value. When we compute QK transpose, we're calculating all pairwise compatibility scores simultaneously. This is matrix multiplication, just as we saw in episode 3. Row 1 of Q, dotted with column J of K transpose, gives the compatibility between tokenized query and token JA's key. Let's compute a few entries explicitly. Row 0 of Q, the, dotted with column 0 of K transpose, also the, 0.4 times 1.2, comma plus 0.4 times 0.4, comma plus 1.2 times 0.8, comma plus 1.2 times 0.8. That gives us 2.56. Now the critical one. Row 2, it, dotted with column 1, animal, 0.55 times 1.7, comma, plus 0.55 times 0.7, comma, plus 1.35 times 1.2, comma, plus 1.35 times 1.0. That's 4.29, the highest score in this row. The same computation fills every cell. Each entry is 1 dot product, measuring how well that query matches that key. Here's the complete score matrix. Look at the row for it. The scores are 3.04, 4.29, 3.61, and 3.10. The highest compatibility is with animal at 4.29. Even before Softmax, the raw dot products already favor the correct reference. This is the signal that attention will amplify. But there's a problem. Without scaling, these dot products grow with dimension dk. If Q and K have components drawn from a standard normal distribution, the dot product has mean 0, but variance dk. With dk equal to 64, the standard deviation is 8. With dk equal to 512, the standard deviation is over 22. Values of plus or minus 16 push Softmax into saturation, where gradients vanish and learning stops. The fix: divide by the square root of dk. Let's prove why this works. Step 1. The expected value of the dot product is 0 by independence. Step 2. The variance of a single product term qi times ki equals 1. Step 3. Since the dk product terms are independent, the variance of the full dot product is dk. Step 4. After dividing by square root dk, the variance becomes dk over dk, which equals 1. Unit variance restored. Let's see what this means for Softmax. Take scores of 8, 2, 1, and 0.5. Without scaling, Softmax gives 99.6% to the top score. It's essentially a one-hot vector. Gradients are near 0. Now divide by square root of 64, which is 8. The distribution becomes smooth. Meaningful gradients can flow. Think of the square root of dk as a temperature parameter, just like we discussed in episode 5. Now let's apply this to our toy example. We take the score matrix from section 3, divide every entry by square root of 4, which is 2, and apply softmax to each row. The result is our attention weight matrix. Every row sums to 1, forming a valid probability distribution. Let's zoom in on the attention weights. Look at the row for it. The weights are 0.19, 0.36, 0.25, and 0.20. The highest weight, 0.3573, goes to animal. The model has learned that it should attend most to the animal, exactly the coreference resolution we wanted. Now multiply the attention weights by the value matrix vive. The output for each token is a weighted average of all value vectors, with weights determined by the attention scores. Let's decompose the output for it. It's a weighted average of all 4 value vectors. The largest contribution comes from animal, with a weight of 0.3573. The contributes 0.19, it itself 0.25, and tired 0.20. The final output vector for it blends information from all tokens, with the strongest signal from animal. Think of attention as a differentiable dictionary lookup. A hard lookup, like a Python dictionary, finds an exact match and returns one result. But it's not differentiable. Gradients can't flow through it. Soft attention compares the query with all keys simultaneously and returns a weighted combination of values. The key word is differentiable. Gradients can flow backward to update WQ, WK, and WV. That's backpropagation in action from episode 4. This isn't replacement, it's refinement. The attention output is a delta E, a change in embedding, added back to the original via the residual connection. It doesn't lose its identity. It gains contextual information from animal and tired through the weighted average, then carries that enriched representation forward. And here's the complete attention equation in all its glory. Attention of QKV equals softmax of QK transpose divided by the square root of DK times V. Multiply queries by keys, scale, apply softmax, then multiply by values. That's all it takes. A single attention head computes one weighted average, but language has many types of relationships: syntactic structure, semantic meaning, positional proximity, coreference links. One head can't capture all of these simultaneously. Multi-head attention solves this by running H parallel attention heads, each in its own DK dimensional subspace. With D model equal to 512 and 8 heads, each head operates in just 64 dimensions. The outputs are concatenated and projected back to 512 dimensions through one more learned matrix, WO. Each head computes its own attention pattern independently. Head 1 might learn to attend to adjacent tokens. Head 2 tracks syntactic relations. Head 3 resolves coreference, linking it to animal. Head 4 distributes attention broadly for general context. Then all 8 outputs are concatenated and passed through WO, merging these perspectives back into the full 512-dimensional space. Research by Clark and colleagues in 2019 confirmed that individual heads specialize. Positional heads dominate in earlier layers. Syntactic heads appear in the middle layers. Coreference heads resolve pronoun links in later layers. Remarkably, Voida and colleagues showed that pruning 38 out of 48 encoder heads drops translation quality by only 0.15 BLU. Most heads are redundant, but the specialized ones are critical. Let's count the parameters. Each head has 3 projection matrices of size 512 by 64, giving 98,304 parameters per head. Multiply by 8 heads, 786,432. Add the output projection WO at 262,144. Total 1,048,576 parameters per layer, approximately 1 million. And here's the beautiful part. 8 heads at 64 dimensions each costs exactly the same as 1 head at 512 dimensions. But it consistently outperforms single-head attention because each head learns in a different subspace. Attention treats all positions equally. It has no sense of word order. The cat sat on the mat, and Matt the on-sat cat the produce identical attention scores without positional information. The solution? Add a unique positional signal to each embedding. The positional encoding uses sine and cosine functions at different frequencies. PE at position pose and even dimension 2, I equals sine of pos divided by 10,000 to the power of 2I over D model. Odd dimensions use cosine. Here's what this looks like as a heat map. Each row is a position. Each column is a dimension. The left dimensions oscillate rapidly. High frequency, capturing fine-grained position differences. The right dimensions change slowly. Low frequency, capturing coarse differences. Why sine and cosine specifically? Because for any fixed offset phi, PE at position pos plus phi is a linear transformation of PE at position pos. Using the trigonometric addition formulas, we can express the shifted encoding as a rotation matrix times the original. Here is the 2x2 rotation matrix. It depends only on the offset phi and the frequency omega k, not on the position itself. This means the model can learn relative position through simple dot products. The full transform is a block diagonal matrix of D model over two independent rotations. Think of it like a continuous version of binary counting. In binary, each bit alternates at a different frequency. The least significant bit toggles every step, the next every 2 steps, the next every 4. Sinusoidal positional encoding is the continuous analog. Discrete bits, 0 and 1, become continuous sinusoids in negative 1 to 1. Each dimension pair is a clock, ticking at a different frequency. Before 2017, sequence models were sequential. RNNs processed one token at a time. Hidden state HT depends on HT-1. You can't parallelize this, and information fades over long distances. Bodenau and colleagues in 2014 introduced attention alongside RNNs. The decoder could attend to all encoder states, eliminating the fixed vector bottleneck. But the radical insight had not yet arrived. The encoder and decoder were still sequential RNNs. Attention was an addition, not a replacement. The radical insight of attention is all you need was, remove recurrence entirely, use only attention. Self-attention is O1 in depth. Any token can attend to any other in a single layer. RNNs require ON steps for the same thing. Let's compare the complexity. Self-attention requires O1 sequential operations. Recurrence requires ON. The maximum path length between any two tokens is O1 for self-attention versus ON for RNNs. Per layer, self-attention costs ON squared times D, while recurrence costs ON times D squared. For typical natural language processing, where the sequence length N is shorter than the model dimension D, self-attention is actually cheaper. The results were decisive. English to German, 28.4 BLU, surpassing all previous models including ensembles by more than 2 BLU. English to French, 41.8 BLU. The base model trained in just 12 hours on 8P100 GPUs. Days or weeks of training compressed to half a day. The paper now has over 173,000 citations, among the most cited of the 21st century. This architecture, the transformer, now powers ChatGPT, Claude, Gemini, and virtually every breakthrough in AI. Let's recap the 5 ideas that make attention work. 1. QKV. 3 learned projections that separate asking, advertising, and carrying information. 2. Dot product scores, measuring compatibility between every pair of tokens. 3. Scaling by root decay, preventing softmax saturation so gradients can flow. 4. Multi-head attention, 8 parallel perspectives, each specializing in different relationships. 5. Positional encoding, sine waves that give attention a sense of where words stand. This is the core of every large language model, 12 episodes of mathematical foundations, each building on the last. But attention alone isn't the complete transformer. Next episode, the complete transformer, where we assemble every piece from episodes 1 through 12 into one unified architecture. The final episode, everything connects.